Hello everyone, welcome to the AI portal, your gateway to the world of artificial intelligence. In this video of the multimodal series, we discuss PaliGemma by Google. PaliGemma is a vision language model that takes image and text as input and produces text as the output. If you want to watch how GPT-4o works with vision, you can click on the top right corner. First of all, let us understand a bit about the architecture. This is a blog written by Hugging Face that clearly illustrates the internal details of PaliGemma. Usually, vision language models that can accept both image and text are trained using the CLIP process. This model uses a very similar technique called the SIGLIP, which is the sigmoid loss for language image pre-training. What is the main difference between CLIP and SIGLIP? Let us understand this with first explaining a bit about how CLIP works. If you see, there are a set of images and there are a set of text. The embeddings from all the images in the training set and the embeddings from the associated text are grouped into a matrix as shown in the figure. The main objective here is to teach the encoders to generate embeddings so that the image associated with the correct text has a high cosine similarity and all the others have a low cosine similarity. If you see for image I1 and T1, for image I1 the correct caption is T1. So I1 dot product of T1 should be high and I1 dot product of T2 should be very low. The loss function is a generalized softmax operation that is based on this exact objective. If you remember the softmax function, it is a probability distribution over all the possible classes. In this case, it calculates the probability of each image being associated with each caption. Now, if your data set is very large, you can imagine how computationally expensive this can become. To solve this problem, the SIGLIP uses a sigmoid loss in place of a softmax loss. It changes the objective to a binary classification problem where the probability whether an image caption is associated with a particular image. This way, the global softmax operation can be avoided, making the training process much more efficient. Now that we have understood this, let's go back to the blog. This is the image encoder part that converts the image into tokens. A sentence piece tokenizer is used to convert the text, and these tokens are appended with some padding so that the length is proportionate to that of the image tokens. All these inputs are fed into the decoder only transformer based Gemma 2 billion model to generate the output text tokens. Please note that PaliGemma is not a chat model, but it works well for one-time questions. So it is meant for tasks such as visual question answering, image captioning, and OCR. It, it was trained on various image text pairs from web pages like Wikipedia. You can see here that the translation API has been used to make the training set multilingual. This model basically comes in three different variants. One is the 224 by 224, 448 by 448, and 896 by 896, and also three different precisions. Unless you have some OCR tasks that require understanding the images in a great detail, this blog claims that there's not much of a difference in accuracy among these variants. But these are the base models. There are also mixed versions that have been fine tuned for specific tasks. They are the ones which we will be testing now. So let's go to this Hugging Face space and see how the model works for different scenarios. Here we upload our image and here we give the prompt. And if you see, we can select a higher resolution model, but right now I'm sticking to 224. So let's get started. Let's start by uploading an image and see how the model understands it. So if you see, I am just uploading the image of scenery and I will ask the model to describe the image in detail. And here I can also change the settings of the sampling, like changing the temperature and also the green and selecting nucleus sampling. So we have this that in this image we can see a building. There are some flowers. There's a door. There's a window. There's water. There's the sky. Yeah, so I was expecting some more details, but I think this is fine for a model of this size. Now let us do again an interesting task of now let us upload a noisy version of the same image and see if the model can separate the noise and still understand what is there in the image. So I'm basically using the same prompt and I click on run. Yeah, so if you can see the output, it's not really the same. So it says in this image, we can see flowers, plants, wall, and water, which is not wrong. But again, it's not as detailed as the ones we've seen in the non-noisy image. Now let us try something like handwriting recognition, and let's upload an image that contains my personal handwriting from my math assignment. So if you see, there is some answers and some mathematical equations. And let's change the prompt asking the model to extract the text from this image. Okay, it says unanswerable. Let's try it out with a higher resolution model. Okay, so since the resolution of the image is high, I don't think it's really picking it up. So it just says one, it continuously repeats the same output. So I think maybe this is not the right image resolution that we need to upload. So yeah, let's try something else. Let's try upload this image and ask for a caption. So I'm asking the model to write a caption for this image. And it says in this image we can see a group of people sitting on the chairs. In the background we can see a shelf, a window, a lamp, a door, a curtain, and a frame on the wall. I mean, that's exactly the description, but here I have asked for a caption, and maybe let's try some other prompt. Let's write caption here and then click on run. Okay, now it really gives an even more verbose description, but not a caption. So yeah, I think that's fine. Now, as a final test, let us try out something like an image segmentation for the same image. So what we do is for getting the segments or objects from an image, you can write detect and what objects you want to detect or segment. So let's say detect people in this image. Okay, so there's no output, but according to this blog, the expectation is that we have some kind of coordinates. If you see, if you say detect entity, we expect to get some y and x coordinates that we will in turn process and see how it works. So here in this, if when they write detect cat, really did detect the cat. Let's try segment and then run it. Yeah, so when we say segment, it did give us some kind of location details, but it didn't really segment all the people there. It only segmented this lady. But yeah, I think it has something to do with these people being kind of at the background. So yeah, these are the outputs for different use cases of this model. Now, since this model has only 3 billion parameters, we cannot really expect it to work at the GPT-4 level. But we can definitely fine tune it to our specific tasks very easily. This model could also be useful when you want your responses to be as concise as possible, especially for things like question answering. Often, larger models give very long answers that might not be needed always. So, in such scenarios, smaller models like PaliGemma might be the answer.